today we are going to solve the spherical shell problem again, a shell with charge Q. And now I'm going to show you speed up how we can solve this very, very quickly using the Poisson equation, lambda square b equals 0. So if you can do that, you can speed up the problem solving, so we can do it in 1 minute basically. Anyway, here's the lambda square operator in spherical coordinates, which is appropriate. And we should also understand that by symmetry, the potential is only a function of r, not of angles or anything like that. So that means we have this, only this term here. So, all right, equals 0. And then you can multiply up this to 0 and it disappears. And then you have this part. But if that is 0, whatever is inside here must be a constant, right? So r squared dv dr is a constant. Call it a. And this is equivalent to this. dv dr equal a divided by r squared. All right. So what is v then for this problem? Yeah, then you realize that v equal negative a over r plus a constant b. So if you take the derivative of this, you will get that. So let's take a look first and solve inside the spherical shell. Okay, obviously a must be 0 because we can't have that term, because we are gonna be able to describe the potential also when r equals 0. So in that case, it will be b. And what constant is b? If you think about charges on the spherical shell and sum them all up, it's always the same distance, isn't it? So it will be q over 4 pi e naught r. That is the constant b. So then we solved it inside the spherical shell, and now let's have a look at the outside. So then we have the general formula here again. The first boundary condition is at the infinite distance, it is 0. So if you look here, that term is 0 then, and then, okay, that must mean that b equals 0 then. Okay. Right. And then another one is this, is a boundary condition. So minus a over r equal what? It's what the potential is here in the neighborhood. And as we already know, it's this is a constant inside the shell, also very close to the boundary here, and it's the same from the other side. So it must be like this. So then we get a equal minus q 4 pi e naught. And then we look, okay, what is the potential then? Now when we determine the a, yeah, is this one. Yeah, so that's the potential outside the shell. So as you see, this is really, really simple to determine the potential both inside and outside. So Poisson equation can be very, very powerful sometimes. Thank you very much.